In this video, I'm going to show you how to test population proportion P. So this is the same the binomial setup. So each trial is with two possible choices, success or failure, with a probability of success is P and the probability of failure 1 minus P, which is Q. So you already know the central limit theorem. Pretty much for large n, if you pull n trials, large n, if the number of trials is large, the sample proportion, which is p hat, is going to be approximately normal with the mean p, and the standard deviation is square root of pq over n. So larger than, better the approximation. So this is the one, the curve we are going to use to test this kind of proportions. In other words, we want to test, see this proportion, say this proportion p, we want to check whether this proportion p is equal to p naught. P naught is a given value, like a 0.2, 0.3, something like that. The alternative hypothesis is that the rate is more than that p naught value, or less than that p naught value, or not equal to that p naught value. Okay, so very much the same three alternative hypotheses: upper tail, lower tail, and two tail. Okay, so so again, this is one of the assumptions. Got to be large n, because this is the curve we are going to use. So we already know the sample proportion is going to follow that. So that's that. So under H naught means that assuming H naught is true, if you assume that this is true, the p value, this p value got to be equal to that p naught value. Okay, so this p value got to be same as that p naught. So same as that p, this value must be p naught, and q is 1 minus p. So that way, so I'm going to say that is q naught. Okay, or 1 minus p naught. So under H naught, assuming H naught is true, so that will follow that distribution. So this is the curve we are trying to see whether they are correct. Okay, so here, in other words, if you get rid of the mean and then divide by the standard deviation, that is the z curve. So the sample z is going to be this one. So this quantity is supposed to follow this z curve. Okay, so supposed to follow this z curve. So it's depend on, so this is the z curve. Depend on the alternative hypothesis, your rejection region is in this side, or for part A, on this side, for part B, so on the lower tail, or part C, there are two rejection regions, one for this side and one for that side. All right, okay. So in other words, at alpha level, so you have, if you're dealing with part A, so you have only one rejection region. You put the whole alpha into one side. So you reject H naught and accept HA if at alpha level, if sample Z, this value, is bigger than that cutoff, Z alpha. Okay, so it's going to be on this side, Z alpha. So this one for part B, so reject H naught and accept HA at alpha level. So in that case, for part B, rejection region is going to be in the lower tail. So leaving alpha to the left. So this is going to be minus Z alpha, which is that. So if it is below that cutoff, you reject and accept HA. So for the two-tail test, so there are two rejection regions, one on this side and one on the other side. So you got to split your alpha into two halves. Okay, alpha divided by 2 onto this side, alpha divided by 2 onto that side. So if that sample Z is either in this corner or in that corner, then you reject H naught. In other words, the test is significant at that level. Otherwise, if it is in between, the test is not significant. Okay, so pretty much this p hat is the sample proportion. Once you pull your random sample out of that, so you have the p hat, which is that the number of S in your sample, number of S values in your sample divided by the number of trials. Okay, so you already have seen that. Okay, so when you say sample proportion, is that the number of S, this one, number of S divided by N, the total number of trials. Okay, so finding the p-value is exactly the same as the other cases. So it's depend on this or that. So you set your cutoff, write on the sample Z and use the Z table to figure out the p-value. All right. So when you look at the assumptions is that the trials got to be, of course, independent binomial setup. Okay, pretty much it's a random sample coming out of this kind of thing, either that way or n independent identical trials. You remember that words we use in the binomial setup, n independent identical. So in other words, that each trial they are totally independent, or the identical means that from trial to trial this part is the same, P and Q. Okay, or you can simply say that is a random sample. Okay, so from this kind of setup. So also this is the other assumption, the important assumption, large n. Large n, for in this case n times p0 got to be bigger than or equal to 15, and nq naught must be bigger than or equal to 15. Pretty much some books use that 10 is also enough. Okay, so either 10 or 15. So it's depend on the book you're looking at. So here's, so got to be minimum 10. Okay, so remember that there was a such condition with the confidence interval before also. Okay, got to be number of the trials got to be bigger than the number of the successes, and number of failures got to be bigger than 15 or 10, something like that. With the confidence interval you had almost the same thing. Okay, but in this case, instead of saying that the number of successes, number of S values or number of failures, so here you have n times p naught and n times q naught. Okay, all right, so that's that. So that got to be correct, otherwise you're going to get invalid results. So for you to rely on your answer, that got to be correct. Okay, so let us look at an example. So this one, so this drugs so has believed to be only 60% effective. So there's a new drug. For the new drug, the question is that is this sufficient evidence to conclude that the new drug is superior to the one commonly prescribed? So the evidence is this. So you look at the sample, 100 people, and suffering from this one shows that 70 received relief, 70%. Success rate is 70%. Okay, effective rate is 70%. So you want to check. So if it is this is for the sample, 70%. So you want to check whether the new drug is going to be effective if the effective rate is more than 0.6, because 0.6 is for the old drug. Okay, so if it is more than 0.6, it's effective. So here, so that's what the alternative hypothesis you want to check, and p equal 0.6. So for large n, assuming this n is large, we can check it at the end whether n is large. Sample proportion will follow this normal distribution. Under H naught, this value is 0.6, this is 0.6, and this is 1 minus p, which is 0.4, and n equal 100. Okay, so the sample Z is going to be this minus that divided by that, sample C. So the p hat, sample proportion, 70 out of 100, which is 0.7. So this is going to be 0.7 put that 0.7 here and calculate that. This is going to be 2.0412. So now the alpha level 0.05, which is the alpha. So from the z table, this is the supposed to follow a z table now. So this got to be alpha because it's only one tail, upper tail. So 0.05, you already know that this cutoff 1.645 coming out of the z table. So this value is bigger than that. So inside the critical region, rejection region. So your conclusion is a reject H naught at 0.05 level. So in other words, the test is significant at 0.05 level. In different words, if you want to say that, the new drug is better than the old drug at 0.05 level. So if you want to find the p-value now, so you got to use the z curve now. So you need to set your cutoff on the sample z, this one, sample z value, and need to get that area. So use your z table to figure out that area, z more than that, which is 0.0207. So this is one tail. So if this is a two-tail test, so you multiply that thing by, because there's another cutoff on the other side, so you multiply by 2. Okay, so so that's the p-value or the observed significance level. So if you want to make your conclusion using the p-value, if you simply say that if alpha level is bigger than that, then you reject the null hypothesis and accept the alternative. Otherwise, you cannot reject H naught. Okay. So in other words, if alpha is, say for example, if alpha is not given, so then you can make your conclusion like that, the way we did it in the very beginning when we look at testing mu. Okay, so check for n. So n times p naught, which is 100 times 0.6, 60 is more than 15, so it's depend on the book you want to check. Okay, so bare minimum you got to have sort of 10. Okay, so 10 or 15. So so here it's depend on the book. Most books use actually 15 anyway. So so n times q naught, 100 times 0.4, 40, which is more than 15. So n is quite large enough. Larger than better, you have a better answer. Okay, but this is quite large enough for you to have some sort of reliable answer. All right, so